Okay. Last time we started, right? We started to look at the, we have a brief introduction for the two types of the convection we're interested. One is one is flat plate, right? Flow over a flat surface. Okay, obviously that's of interest. The other is flow in conduit, right? In internal flow in the pipe. There are two types of different convection problems. Okay, so we're going to spend several classes on these two topics. Okay, so I think we started talking about the flow boundary layer on the flat surface, right? That's for laminar flow. So we have all those solutions, analytical solutions, laminar boundary layer. I'm going to introduce also today the thermal boundary layer, right? Temperatures, and then we will talk about the turbulent boundary layer, the flow boundary layer, as well as the thermal boundary layer for the turbulent flow over the boundary layer, over the flat plate. Okay. Do you still remember we talked about the flat plate? What does the turbulence on the flat plate look like? You know, it's not like start from the beginning, right? Every flat plate boundary layer, always at the beginning of the plate is laminar. When the plate getting longer, the later part of the boundary layer is turbulent boundary layer. Did we talk about this, mention this last time? I think we did, right? I have some drawings, I remember. Like this, right? At the end, if it's long enough, the plate is long enough, then become turbulent boundary layer. So it's connected, okay? It's not like you have turbulent boundary layer start from the beginning of the plate. No, unless you have tripwire or something like that to start the turbulent immediate. Otherwise, regular plate you always have laminar boundary layer first, then it's turbulent boundary layer. Okay. So there's the Reynolds number, right? Do you remember how to calculate the Reynolds number for the boundary layer flow? Yeah, here's the equation, right? Reynolds number, free stream velocity times the length. Okay, x. This is the local Reynolds number. So every different location you have a x, right? So in that sense, you have a Reynolds number. Okay, so when Reynolds number reach to 5 by 10 to the 5, then it start to show turbulent structures. Okay, so that's the Reynolds number. In the duct flow, you also have different Reynolds number, right? So today, let's continue on that flat surface, laminar boundary layer over flat surface, right? So we introduced those characteristics, but we didn't introduce anything in specific about the boundary layer. So I think the important thing you want to know is the boundary layer thickness. I said delta. Okay. So boundary layer thickness, you have to calculate the boundary layer thickness. Then you know how thick the boundary layer is, right? You can even draw the boundary layer like this. Otherwise, how do you know what the boundary layer look like, right? So I think that's the first thing you want to know. Okay, that's the equation. Let's skip those derivation. Let me just directly give you the equation. Okay. Boundary layer thickness for the laminar flow equals phi times x over square root of Reynolds number x. Okay. So what does that mean? Reynolds number x and the phi x. Okay. So that in the denominator in Reynolds number, there's also an x, right? But it's in the power of half. So in the numerator, x in the power of 1. So you know that the boundary layer thickness will be increased with increase of x. Does that make sense? Okay, that's the laminar boundary layer thickness. So that tells you at every different x, this is the x direction, right? And every different x, you should be able to calculate a boundary layer. So you have, if you know your property of fluids, which is in the Reynolds number, right? So if you know the property, you should be able to calculate. If you know the speed, the main free stream velocity is also in the Reynolds number, right? So if you know the speed, if you know the property of the fluid, you should be able to calculate a boundary layer thickness at every location. Okay, if you have Excel in your computer, you can actually plot the boundary layer to see what does it look like. Okay, based on your calculation, you know the thickness at every location, so you can actually plot it. Okay, so this is the boundary layer thickness. By the way, do you still remember how to define boundary layer? What's the criteria we use to define this border? Anybody remember?
It was the velocity of the boundary layer over the velocity of the free stream has to be less than like 99% of, yeah.
Yeah, I think
No,
within,
you know what I'm saying.
under, yeah, I know what I mean. Under the boundary layer, it will be less than 99% of the free stream velocity. How about that? Under the border, right? Inside the boundary layer, the speed will be less than 99% of the free stream velocity.
There you go. That sounds like that.
Yeah. And outside, it's basically it's free stream velocity. Okay, so that's a special layer. Okay, it's boundary layer. So the thickness can be calculated by this equation. Okay. Then the thermal boundary layer. There's also a thermal boundary layer thickness. Let's say delta T. Okay, it's different. It's basically it's the thickness is different, so it may be bigger or small. Okay, let's see. It depends on the property. Okay, let me see if in the textbook it gives you a drawing. You know, it's a special condition. For example, it's the plate. If the plate is not fully heated, if it's plate starting from a, you heat it from here, then it's a different equation. So that definition of that. But if it's being heated from the beginning, maybe this is a thermal boundary layer thickness. Okay. In the figure 5.9 in the textbook, page 233, it shows a more general situation, which in the this is the, okay, and there's the X0 here, but please understand what X0 means. So it means it's being heated from the later portion of the plate. It's not from the entire plate. Okay, so if that's the case, you have a set of equation. But if you heated the entire plate, just like a regular case, you have a plate, it's heated, all of them. Then the boundary layer, thermal boundary layer, will also start from the beginning. Okay, that's. When you read, there are a lot of many equations there, but just sometimes some equation you probably want to read yourself. Then just make sure you understand that X0 means the portion in the front is not being heated. Okay, so thermal boundary layer. The equation is equation 5.38. Okay, so thermal boundary layer over laminar on the flow boundary layer. So you need to know the flow boundary layer. We give a name called zeta. Okay, is that the letter zeta? Anybody? I'm terrible on those Roman or Greek letters. Is a Hurricane Zeta? Tropical storm Zeta recently hit New Orleans. Is that the letter? I don't know. Maybe you're not much better than me. Okay.
Dr.
Yeah.
What page are you on in the book? I'm trying to find it, but
it's page 235.
Okay. Thank you.
Okay, you're welcome. Equation 5. Yeah, you probably need to pay attention. The book has so many equations, yeah, and so many derivations. Okay, I skip most of them. I just I dig out those important ones for you to use. Okay, I think we don't have enough time to go through all the derivations. Okay, for this in this class, it's a shorten the semester. So let me give you all those equations that be useful for your engineering application. How about that? Okay, so the zeta is the ratio between the thermal boundary layer and the and the flow boundary layer. So in that sense, the flow boundary layer is important to know also, right? You need to know the flow boundary layer in order to calculate the thermal boundary layer. So it's equal to 1 over 1.026. Okay, we're going to introduce something called Prandtl number. Okay, this is the equation, but you need to know what the Prandtl number means. PR is Prandtl number. That's a very important dimensionless number in heat transfer. Prandtl number is viscosity over alpha. Do you by chance know what is alpha? Alpha usually we use for the thermal diffusivity. Thermal diffusivity. Thermal diffusivity is K over rho Cp. Okay, so because in the numerator is kinematic viscosity. So if you use dynamic viscosity, it will be viscosity over rho. So the rho and the rho can cancel, right? So it will become viscosity times Cp over K. Okay, so I think that's a Prandtl number. Prandtl number is also in the equation with 5.39, right? Talk about the Prandtl number. Actually, 5.37 it is also the Prandtl number. Okay, but what's the meaning of Prandtl number? Okay, so I guess I need to introduce to you, but right now, but later you probably will have, when you do more problems, you will have more understanding of this Prandtl number. Prandtl number is the ratio between the flow diffusivity and the thermal diffusivity. Okay, viscosity nu is the diffusivity of the flow. So look at the, you probably don't know the momentum equation for the flow. Actually, viscosity is in front of these two diffusivity are in front of the same second order derivative. Okay, both velocity flow equation and the temperature energy equation in the differential form, they are all the transport equations. They have the convection and the diffusion terms. Diffusion terms are the second order derivative in the equations. Okay, so but they're the coefficient in front of the diffusion terms. So they call it diffusivity. Okay, flow diffusivity and the thermal diffusivity, which means, you know, the temperature change is due to the gradient. You know, if you have a high gradient, if you have a gradient in the temperature field, which means you have a high temperature and a low temperature, okay, then the heat transfer always go from high to low. So the high temperature will be diffused into surrounding low temperatures. So velocity is the same. Velocity, you have a high velocity, you have a jet stream, for example. If a jet coming out of the injection port, it's concentrated the flow. But when you go far away from the jet port, gradually it becomes diffused, right? Everywhere you seems like have a little bit flow. So the flow phenomena, the velocity is also also has a diffusion characteristics. Okay, that's why those equations are similar. Okay, flow equation and the temperature equation, energy equation. So the diffusivity is a coefficient that characterizes how fast the diffusion will happen. Okay, so Prandtl number is the ratio between the flow diffusivity, which is the viscosity, over the thermal diffusivity, which is alpha, is K over rho Cp. Okay, so this is the background. Okay, so but I didn't provide you that differential equation is super long. So there's 3 equations for the velocity and the 1 equation for the temperature. Okay, but just let you know, these are the diffusion coefficients. Okay, but I want you to know that diffusion is one of the mechanism for heat transfer. Okay, basically there are 3 mechanisms we learned here. One is convection, the heat transfer due to the flow. Okay, one is diffusion. Okay, diffusion is anytime if there's a gradient, you have a high temperature, you'll have low temperature, high velocity, low velocity. The velocity will transport, the temperature will transport. Okay, we transfer. Okay, that's called diffusion. Okay, so and also radiation, right? We don't care too much about radiation. So these are the diffusion coefficients. Okay. So this is the Prandtl number. So there are properties. You should be able to find the Prandtl number. You find the Prandtl number, you should be able to find out the zeta here. Okay, the zeta is the ratio between the thermal boundary layer thickness and the flow boundary layer thickness. So then you need to find out the flow boundary layer thickness. Based on this ratio and the zeta, you should be able to find the thermal boundary layer thickness. So this is the process, okay? Is that good? Seems like there's no direct equation for the thermal boundary layer thickness, okay? But we have to go through this, go through the flow, okay? Any questions so far? I'm afraid I talked too fast and didn't catch up. Any question? You can slow me down. So far, so good. So now we learned how to describe the both boundary layers. Okay, one is flow boundary layer thickness, and one is thermal boundary layer thickness. Okay, so I think I need to tell you how to. We know 99% of the velocity is the flow boundary layer. So what about the thermal boundary layer? Thermal boundary layer is 99% of the temperature. Okay, so the outside the temperature is the flow temperature. Inside is different. Okay, either higher or lower. Okay, basically, let me put on the same page. It doesn't need a lot of space. Okay. Okay, let's change it to a new page. The thermal boundary layer. Okay, the condition of the boundary of the border is dt over dy equal to 0, or t equals to, let me see, or t equals to t infinite. I say equal, you can say it's 99% close, okay? So then this is y is on the thermal boundary layer, okay? Does that make sense? But we're talking about the iso temperature condition. So your temperature T equals to T, whatever water temperature, constant water temperature at y equals to 0. So these are the boundary conditions for the thermal boundary layer. Okay. Are you sure that you don't want me to explain more? Is that clear to everybody? Okay, everything we use here is math, okay, equations, okay. So you have to fully understand the equation to fully understand the physics. Okay, that's the difficult part of the fluids and heat transfer. Okay, really rely on the math. Okay, so at the wall, T wall, right, temperature, but at the thermal boundary border, at the y equal delta T, then the temperature either you say temperature is outside temperature or 99% close, okay? Or you can say dt dy equal to 0 because the gradient, if its velocity becomes same as the outside temperature, then velocity don't change. Then start from the border, dt dy start to become 0, okay? That makes sense? So for the thermal boundary layer, it could be still just similar to that. It's a low temperature, or maybe even a high temperature than low temperature. Usually, no, that I don't want to use arrow. It's confusing. Arrow is a temperature, okay? Temperature is not a vector. I'm not supposed to use the arrows, but for your understanding, okay? So this may be the temperature profile along the y direction, okay? So on the wall, you have a T wall here, high temperature. Then on the thermal boundary layer, on the border, they become T infinite, which is lower. Okay, and start to not changing anymore. It's become 0 gradient when you reach to the boundary layer border. Okay, is that good? Or it's the other way, because temperature is really velocity. You have to be 0 velocity on the boundary. Right? Always like this. It could be other way. Maybe there's a low temperature. The wall is cooled, right? It's possible. Opposite direction, opposite way. So maybe the low temperature on the wall and high temperature on the surrounding, on the outside. It's possible. But boundary layer still, when it reach to the outside velocity, the boundary layer ends. Okay. Okay. If you don't have any question, let me introduce one more. This is the boundary layer, right? Boundary layer thickness. Okay. So what about what's really important for us to know in heat transfer? For example, we design a heat exchanging surface. Okay. Let me ask you this. In engineering, you are engineer, design a heat exchanger surface. Okay. You try to use flow, okay, cross flow heat exchanger. You blow liquid or blow flow to go through, let the flow go through the surface to remove heat. Okay. So what do you really need to know for the design to say this heat changer surface is effective or not? What numbers you need to know, or what property or what coefficient you need to actually find out?
The K value?
No, it's not K, convection, come on, convection. K is the conductivity in the solid material, right? Now you have this is the convection heat transfer problem, right? You let the flow go through the surface, flow through the surface to carry the heat away. Okay, that's the mechanism of the convection. So it's a convection. What you really need to know to determine is this convection situation effective or efficient? Oh, which coefficient you need to know? H, right? Definitely, absolutely. You need to know H in terms of heat transfer. You need to determine H in terms of the characteristic of heat transfer. And also you need to determine the shear in terms of the pressure drop, pressure loss. Okay, that's a big picture. I'm deviated a little bit from the textbook. I think these are the important practical information for you to know. Now you know the boundary layer thickness. You can draw the boundary layer for thermal and the flow. Okay, no problem, good. But that means nothing to you right now. Okay, you know what the boundary look like. So what? So your design, right? You're an engineer. You try to design something. To design this, you're blowing flow to it. You let the flow passing through the surface. Your goal is to transfer heat, right? And then if you design a scenario like this, what kind of fluid you want to blow to it, and what's the speed you want to blow to it. Okay, this is your design, right? Okay, so then you need to measure is your design effective. Okay, so you need to determine these two things, okay, to show your design is effective in removing heat and also save money. Okay, the first item H here is to see how effective it removes heat. Okay, the second item here, you have to determine shear is to know how much pressure drop it will cost for this flow goes through it. And the pressure drop is really important. It's related to the money. Okay, because you have to pump the flow. It won't move by itself. Okay, you have to drive it. You have to use a pump, a compressor, whatever. You have to a fan, or you blow it to it, or blow liquid, flow liquid to it, right through it. So you need energy. You need the electricity bills. Okay, so how big a pump you needed to make it happen? It's all money. Okay, so less shear is better. Okay, less shear, that means there will be less drag. Okay, less drag force then leads to less pressure drop. Okay, so I just want to emphasize here, don't just look at H. You can achieve any H you want. Okay, it doesn't matter. Okay, if you have if the U.S. government is behind you, NASA is behind you, you have billions of dollars to design you can design anything. Okay, so it will make it happen. Whatever heat transfer, you want to increase heat transfer, I can increase it for you. Give me money. Okay, but that's not really the usual practice. In industry, we always want to look at how to save money. Okay, with more, we call it efficient, right? To achieve the goal with less money spent. So you also need to consider the shear stress. Okay, most of the surface, if you enhance it, for example, you put the fin on the surface, you put the roughness on the surface, sure, you increase the area, you will increase the heat transfer. H will increase, that's good, but you will also increase the shear because you have roughness, it's not smooth anymore, the surface. So it will have friction. So the money will increase, okay? The cost will increase. So you probably better, it will be better for you to keep a balance, okay? And certain goal to reach certain H, but also you don't sacrifice too much of a pressure drop. Okay, so that's the important thing you need to know. So H, we have equation for H. Let's say our equation for H is equation 5.40. Okay, I think I need to use another page maybe. Okay, hold on, give me a second. I think I reached to the end of this file. Let me save it and create another one. I have another one opened. Okay. Okay, now let me give you H equation. H is 5.40. Okay, so 5.40, this is the H equation. 3 over 2 K over zeta over sigma. Oh no, I'm sorry, delta. Zeta times delta is what? It's actually thermal boundary layer thickness. Remember that equation we have? The ratio, zeta is the ratio between thermal boundary layer and the flow boundary layer, right? So this is the equation. But so in that sense, you see, that's important to determine the thermal boundary layer thickness, okay? This is local. So just like the flow boundary layer, thermal boundary layer thickness is also like this, right? Increasing. So basically, the H is not a constant, depending on how thick the thermal boundary layer is on that particular location. So H changes. You have to remember, know this. H is not a constant when flow goes through the heated surface, okay? There are some correlations also. So you can implement, how to say, you can substitute the delta T equation into this equation for H. It will become very long. Then it becomes 5.41. Okay, 5.41 is for a general equation with x0 there. Remember what is x0? That's a non-heated portion, right? So, but for the heated portion, it will be shorter. You can substitute that. I think we will have, let me see, do I have a, I think most of the time we have the equation without x0. But it doesn't matter. You can just substitute that equation delta T I give you. Okay, thermal boundary layer thickness into that. So 1 over 1.026 Prandtl number to the negative 1/3. That's the thermal boundary layer thickness, right? Just substitute that. You will have the equation for H if the entire plate is heated, okay? 5.41 is the general form with a portion x0 in the front. Okay, that's also for H. General with x0. Okay. So in the industry, in the heat transfer industry, so we always use Nusselt number. Do you know? Oh, you probably don't know. Never know. This is the heat transfer class. You never had a heat transfer class before. Okay, Nusselt number is a dimensionless heat transfer coefficient. It's a dimensionless H. Okay, so it becomes H. So here H should be Hx. It's not a constant. Times x divided by k. Okay, so it's dimensionless convection heat transfer coefficient. It's a ratio H over k. Okay, conduction. Okay, so then you will have, if you substitute this into this, you will have a Nusselt number equation, right? Pretty long. 5.43 also is with x0 there. Okay, if x0 is not there, then it's just 0. Okay, it's just 1. So you don't have that power. I can write it down. Without x0, just Nusselt number will be 0.332. Prandtl number 1/3 times Reynolds number 1/2. Okay, that's it. If you don't have the x0, if it's 0, then the rest part is gone. Okay, so this is just the equation for the entire heated plate. Okay, so equation 5.43 is just like 5.41 is for the Nusselt number for the plate with x0 in front of it, non-heated area. Okay, but we usually we don't use that. We use this. Okay, So H equation, I can even write it down for you. You can use either one, okay? It doesn't matter. In industry, in the convention, people use Nusselt number. If you work in industry, you will see Nusselt number all the time and not directly see the H, but it's okay. I can provide you with the H equation. Okay, one thing is these equations are not empirical solution. It's not from experiment. Although you look like a 0.332, something like that, it's analytical solution, okay? That's laminar flow, so it's analytical solution. You have analytical solution for laminar problem from directly solving the differential equation, okay? This is a 1 over Reynolds number, right? Oh, this is, yeah, it's different, slightly different with Reynolds number. Okay, so that's the equation. These are for the entire plate, heated plate, uniform, okay? Okay, so you have to know the conversion. Okay, I'm guarantee you will see Nusselt number in your work, okay? If you work heat transfer problems in industry. They don't usually do heat transfer coefficient. Then you can easily convert, okay? So Nusselt number and heat transfer coefficient are the same thing, convection heat transfer coefficient, basically. One is dimensional, one is dimensionless, okay? So that's the difference. So all of them, both of them, you will see they are not uniform, right? If on the, because of it's actually related to the X, okay? So related to the Prandtl number. So they are not uniform, okay? It's actually changing along the plate. So I think in industry application, in the practical application, we really don't want to see non-uniform stuff, okay? So if it's non-uniform, we try to make it average, okay? So you can integrate it, but basically, you know, it's no fancy here, because then you have a surface, you have a dx, okay, you have dA, right? It's dx, so you can integrate it, the Nusselt number along dx, entire plate, along the length of the plate. So if you integrate it and then divide by the area, then divide by the length, they become average Nusselt number or average heat transfer coefficient, okay? I know you hated to do the integration, so let me just give you the equation, okay? After you do the integration, it will become 0.664 Reynolds number L to the 1/2, then Prandtl number to the 1/3, okay? So notice this is the Reynolds number L. That's the overall Reynolds number. So it's the end of the plate. Use the length of the plate to find the Reynolds number. Okay, the length, total length of the surface to find the Reynolds number. Then that's the Reynolds number used here for average Nusselt number. That's your average heat transfer coefficient. If you want to know average H, then you can just apply this equation. You should be able to find average H. Okay. So average H times area times delta T then become your total heat transfer from the surface to the fluid. Okay, it's a total heat loss. Okay, do you see the picture here, big picture here? So many equations. Now it's become, I totally believe it's not difficult, okay? It's just tedious. You have a lot of equations to look at. Okay, so I don't think I have time to give you an example, but let me give you the equation for the shears. Okay, so now this is the H, Nusselt number. You determine how effective your heat transfer surface is, right? So how effective heat transfer is on a surreal surface. Now I need to give you the shear. Now you need to know, okay, how much loss I will have. Okay, how much pressure loss we have. Shear equals to, first of all, equals to half rho velocity square. This is the free stream velocity square times area times something called skin friction coefficient. Okay, skin friction coefficient. Okay, this is the average skin friction coefficient. I use a capital letter. That some people call it the friction coefficient. Okay, well, you know, by convention, a lot of people call it skin friction coefficient, CF. Okay, CF this is average CF. Okay, again, average friction coefficient along the plate is 1.33. You probably need to, this equation is not on the textbook. Maybe it's on, I didn't find it. Okay, easy. depending on the flow Reynolds number, right? So it's okay. There are also something called a lowercase cf. It's local skin friction coefficient. So just like the heat transfer coefficient, these are the pairs. Okay, if you look at heat transfer, you look at the cf. Okay, you look at heat transfer coefficient, you like cf is local. It's 0.664 over Reynolds number 1/2. Notice this is the local Reynolds number. This is the overall Reynolds number at the end. Okay. Okay. So it's also based on the Reynolds number. So on any given location on the plate, you should be able to calculate this local skin friction coefficient. You also should be able to calculate the local heat transfer coefficient. Okay, on any location. Okay. So local heat transfer coefficient and skin friction coefficient, you can calculate based on these equations. You can also calculate the average heat transfer coefficient or Nusselt number, and you can have calculated averaged local average skin friction coefficient along the surface. So these are the pair. So as an engineer, you design some heat transfer surface. These are the pair you need to determine. Okay, H bar or Nusselt number bar average. Okay. And the average skin friction coefficient. One bigger is better. H, you have a bigger H, bigger Nusselt number is better. Then you have a bigger CF is bad. Okay, you have a lower CF, it will be better, will be less friction. Okay, so these are the two, the trims you always want to consider when you design something. Okay. So I guess that's my introduction here on the laminar boundary layer flow over a flat plate. Okay, these are the important informations you need to know. I would suggest you remember these things. Okay, these equations if you can, but if you cannot, that's fine. The Nusselt number equation probably is look pretty messy. Okay, but okay. So with this, we can do some calculation, do some example problem. Let's leave it to Monday. Okay, so. Oh, okay. No, I look at time wrong. It's 11:38, right? Our class ends on 11:50, right? So I have time. Let's do one example. Let's do one example. Okay. Let's do a simple one first. Example 5.4. Okay. Example 5.4. Okay, let's read the problem. And by the way, any questions so far? So I have time. I can entertain a question or two.
There's just a lot to take in with all these equations. I'm not really sure what's
Oh,
used
no,
for where.
listen. It's a lot of questions, but you have to remember. See, I'm telling you the trick. You remember the concept here. What do you need to remember? What variable you need to know if you want to design a heat transfer surface? Answer my question. What variables you really need?
You need H.
You need H as well as
Tau.
tau. You only need the two things. Okay. Now, just also you need the delta because the boundary layer thickness will be used in the calculation here, right? So you probably need some. So, but that's all right. So you need the H. Remember, H and the Nusselt number are the same thing. Okay, just remember this. They are the same thing. Okay, one is dimensional, one is dimensionless. Okay, can you remember that? So just try to make them together. Okay, H and the Nusselt number. Doesn't matter. If I know one, I know the other. Okay, so still end up, you need to just know two things before you can make a decision. Okay, H and the CF. Okay, CF I showed here because based on CF you can calculate the tau, the shear. No big deal. Okay, this is just the equation. Okay, so in your mind, it's basically that's two things. If you want to say three things, fine. The boundary layer thickness, both flow and the thermal boundary layer thickness. Okay, there are always equation there. Okay, don't worry about it. You have equation. You don't need to invent any equations. Okay, so most of the time, what's important for you, for the engineer in practical practice, is the average value. Okay, average Nusselt number. and the average skin friction coefficient. Okay, so let me ask you, do you know, if you know the average skin friction coefficient, can you calculate the shear? Do you know that? If you don't know, you can say, hey, that's the equation. I have that equation. Half rho V squared, half rho U squared times area. That's it, times CF. Okay, I remembered it. Okay, shear part, no problem. So if I know the Nusselt number, do you know how to calculate the heat transfer rate? Yeah, yes, I can. Average Nusselt number. I can find my average H. Okay, HA delta T. That's it. That's my total heat transfer rate. That's it. That's all you need to know to make a decision. This plate has good heat transfer. This plate has very good shear loss. That's it. That's the only thing you want to tell your boss or tell your client, okay, for making the decision. Okay, so this is just a check. You have to have a bigger picture first. Have the bigger picture. What do you really need to know from this class, from this topic? Okay, I need to know boundary layer thickness. I need to know H. I need to know CF. Okay, that's all I need. Okay, so focus on these. Okay, is that good? Okay. Well, I'm trying to teach you something like share with you some of my learning experience myself. Okay, you know, I'm not a very good student when I was in college. I know I skipped classes too, just like you guys. I understand. But the final exam. So what did I do? I need to pass it. I need to get good grade, right? So I kind of like know how to find a way to focus on the important things and try to remember those things, and then I try to do it well in the test. Okay. Eventually, I find out how to say this. Eventually, I find out that the skill for, you know, to do well in the test. It's also similar to the lifetime experience, like tasks. You also under pressure, you do a test. You know, you want to focus on important things, right? You want to focus on the big picture, focus on the important things. Then rest of them are easy. Okay, I think the difficult part always doing a job or doing whatever project is at the beginning. You don't know what to do. Okay? You have no direction. Okay, very painful. You know, you really struggle. And I did the same. So kind of, I feel my experience is you really have to have a bigger picture of a topic, of a material. Okay, what is it used for? What's the purpose? Why I'm sitting in class, spend money, spend time to learning heat transfer? Okay, you have to focus on the purpose. Then go back to see, okay, can I learn those stuff to serve my purpose? Okay, so that's my top to bottom, you know, learning procedure. You know, try to have the big picture, have those goals. You know, what you need to learn, then try to memorize the detailed things later. Okay, so yeah, okay. Let's still look at. I have 6 minutes. Let's still look at the example 5.4. Okay, so assume the plate is heated for the entire surface. You have a plate and a heated, okay, entire surface. You have a thermal boundary layer, and the temperature on the wall is 60 degrees. Okay, calculate the heat transfer in the first 20. Okay, heat transfer in the first 20 centimeter, and in the first 40 centimeter. Let's say this is the 20 centimeter. 40 centimeter. Okay, I want to know the total heat transfer. Okay, what do we start? It didn't ask me the friction, right? So what do I need to find?
You need to find H.
Yeah, find H, average H, basically. Okay, or average Nusselt number. I think probably we want to start from average Nusselt number. Okay, so look at the Nusselt number equation here. Okay, 0.44. You need to know a lot of properties. Okay, Reynolds number. I hope you already remember. Prandtl number. What is Prandtl number? That's a ratio, right, between that thing. So probably you need to calculate the Prandtl number first. So a lot of property you need to have. So, but in order to find the property, that raises a question. So I have the temperature here, 60 degrees. What is the outside temperature? 27 degrees. Okay. Okay, so hey, the flow is 27 degree, but here the heated was 60. So in between, yeah, probably it's between 27 and 60, right? Is that right? So what temperature I use to find the properties? That's a big question, right? You have a lot of property to find. You have to find the viscosity, you have to find the K, you have to find the Prandtl number, you have to find the CP, okay? All those things. Is that right? So what temperature? Are you 27 or are you 60? Anybody? Educated guess, we have to use something called film temperature, okay? We have to, you know, it's not wall temperature and the flow temperature, it's the average, okay? So it's called film temperature. So we use that film temperature to find the properties, okay? In the boundary layer heat transfer problem, always use this average temperature. That makes sense, right? You don't know which one to use, so how about average? It's probably similar. Inside the boundary layer should be, you know, in between 26, 27, and 60. Okay, so with this temperature, you should be able to find the viscosity. You find the K, 17.36 times 10 to the negative 6 meters square per second square, meter square per second. K is 0.022749 water meter C. Prandtl number is 0.7 for the temperature of air, and the CP is 1.006 kg times C. Okay, with this information, we should be able to use the average skin friction, average Nusselt number, this equation. You see Reynolds number, Prandtl number are all there, right? So our average Nusselt number for the 20, Nusselt number for the 20 centimeter, okay, 20 centimeter is that given? 44.7. Okay, no unit. Again, Nusselt number, no unit. Okay, dimensionless. So you should be able to find H, average H based on the Nusselt number, and the Nusselt number times K over 20 centimeters, 0.2, right? Okay, so it will be 6.15 watt meter square C, okay? Oh, so total heat transfer. H A 60 minus 27. No, minus free stream velocity, free stream temperature. Okay, area, I think it's given, right? Area is to the 20 centimeter. So will be 20 centimeter, 0.2 times 1. The other dimension is the unit. Okay, infinite long, it didn't say. So the unit length along the Z direction, along the direction in the paper. So 0.2 meter square. Okay, you know this H, you know this. So you should be able to calculate the total heat transfer rate is 81.18 watt for the 20 centimeter portion. Okay, I think the 40 centimeter portion is the same. Just repeat this process. Okay, any questions? Is that good for everybody? Okay, so just know how to apply those equations. We can talk a little bit about this next class. Okay, give you more examples on how the detailed calculations. Okay. Okay, so that's it for today. If you don't have any questions, we'll continue next time. Have a good weekend.
You too.